All right, properties of matrices. Let A, B, and C be matrices whose orders are such that the following sums, differences, and products are defined. So that means we can actually do that. Remember when we do matrix multiplication that we have to check the orders of the matrix and make sure that the two middle numbers, the number of columns in the first matrix matches the number of rows in the second matrix. So they're saying it's already defined, you already know that. The commutative property of addition does hold. Matrix A plus matrix B will equal the same thing as matrix B plus matrix A. But as we talked about, not multiplication. It just doesn't work. You might find one case every now and again that gives you the same answer both ways, but generally there's something special about it that makes that happen. The identity property, we do have a matrix filled with zeros that we can add to something and not change its identity. But we do know that the identity matrix with multiplication has to work backwards and forwards. It has to work in front, so multiplying on the left-hand side, and it has to work multiplying on the right-hand side. And our identity matrix has ones on the mean diagonal and zeros everywhere else. Distributive property, multiplication over addition. Now, this is a big deal. It doesn't look like it when you look at this property, but notice that our A is on the left-hand side of these parentheses. That means when you distribute it, it must be on the left-hand side of each one of these. That's really important. Same thing down here. Notice that this C is on the right-hand side. Because order matters with multiplication, that means it has to be on the right when we do that distributive property. So AC plus BC. Order matters when you're talking about multiplication of matrices. The associative property over here, addition, it doesn't matter which one you have first. That makes absolutely no difference. But even though we're showing this association piece here, notice that it's still A times B times C. So we really haven't changed the order by just changing which two we multiply first. So associative property does work for matrix multiplication. Inverse property, you have A and then you have its inverse matrix, which is basically just the opposite of everything that you have in matrix A. But then for multiplication, we talked about how if you're going to have an inverse, it has to work both on the right and the left-hand side in order for it to be an inverse. And these lines, in case you forgot from Friday, because you got out in the nice sun and didn't think about math all weekend, stand for determinant. So the determinant cannot be zero for those matrices. And then again, order is going to be important when we distribute these. So A on the left has to be in that order when we distribute, and then C on the right has to be in the rightmost position when we do that multiplication. So the properties are a little different than what we just know for overall properties of numbers. Now, applications, well, we can go back to the G word, geometry, and talk about how to use matrices to reflect things. So points in the Cartesian coordinate plane can be represented by a little 1x2 matrix. For example, if you have the point 2, -3, you could represent that as the 1x2 matrix. 2, -3. Thank you. We can calculate the images of points acted upon by some of the transformations studied in way back in section 1.5. I would think more often than not you're just remembering what you did in geometry. So using matrix multiplication as we're going to see. So it says, we want to reflect with respect to the x-axis as matrix multiplication. Prove that the image of a point under reflection across the x-axis can be obtained by multiplying by this matrix. So I start thinking, all right. Visual here of reflecting across the x-axis. So I take some point xy up here, and I reflect that across the x-axis. That's going to be equal but opposite down here. So it's still going to be x, but it's just going to be a negative y. So if when I do matrix multiplication by this matrix, it gives me x negative y, then I know it's going to work. So I think, well, I'm going to have to just start with my normal point up here, which was just xy. But I want to write that as a matrix. So it's a little basic 1x2. And then I want to show, if they said that this works, I want to prove this by actually doing the math and getting x negative y. then I know this is really going to work. So let's see if it works. Now, we go back to the orders, and we realize this was 1 by 2, and this was 2 by 2. So can we actually do that multiplication? Sure can. 2's in the middles are, in fact, what are we going to get for an answer? A little 1 by 2. Those two outside numbers tell us that. So 1 by 2. So far, so good. That's what we needed. So let's see if this will give us what we want. Every time. All right. 1 times x is x. Y times 0 is 0. That's going to be x. That's good. We needed that. X times 0 is 0. Y times negative 1 is negative y. There's our proof right there. We got what we needed. In order for us to reflect over the x-axis, the y has to become negative. And we multiplied by this, and it did. So that's our proof. It's not the, again, formal proofs that we did in geometry, but it's an algebraic proof using matrices, and it works. So now, on to all the good stuff in 7.3. That brings us to exactly why we learn matrices in the first place, why we do a lot of ordering of numbers. So no matter what, now you'll be able to finish. If you found a couple that had you stuck on yesterday's. So multivariate linear systems. Boy, does that ever make us think, wow, that sounds really complicated. Multiple variables. Been working with multiple variables, but most of the ones they've had us do so far have just been the x and y. Now we're going to start introducing z and w. So going from one-dimensional systems to two-dimensional systems, now talking maybe in 3 dimensions or in some cases 4. So we're going to be able to solve systems of equations using all kinds of different methods when we get done today. We're going to talk about the triangular form of linear systems, Gaussian elimination, which is something that you usually study in college when you're dealing with matrices, elementary row operations, and what's called row echelon form. Calculator, we're going to find that listed as REF for row echelon form. And then the better one when you want to solve, which is reduced row echelon form. And on our calculator, that's going to be REF. But again, we need to know how to do all this stuff by hand for the non-calculator portion of the test. You just need to know there's also calculator steps to do that. Inverse matrices and apply matrices to model and solve real-world applications, which will be tomorrow, I'm certain. So, multivariate linear systems and operations is where we're going to start with the triangular form for linear systems. Methods for solving linear systems, whether or not it's first degree for 2 variables, which was our x and y's in section 7.1, can be employed to solve equations with more than 2 variables. So going from 2 dimensions to 3 dimensions. And the goal of the elimination method is to rewrite the system, rewrite that system. And that's so that it is solvable very easily. As an equivalent system of equations whose solution is obvious. We really want to get to the point where when we're going through this, we see, oh, x is 5. If you know x is 5, then you can find all the other stuff. That's when the solution is obvious. 2 systems of equations are equivalent if they have the same solution. Triangular form of a system is an equivalent form for which the solution is easy to read. So, really when we're solving these, we want to think of an upside down triangle, because we're going to have the toughest stuff up at the beginning. And we're hoping that it's going to form an upside down triangle, and we're going to get down to, hey, z equals 5. And then we could just back substitute and get all of the answers. So that's why it's called the triangular method. Triangular form allows us to solve the system using substitution. Hopefully, that makes things fast and easy for us. So think upside down triangle as you work through this. Most complicated stuff at the beginning, easiest stuff at the bottom. Now, it says solve the system. X, Y's, and Z's. Oh man, this is going to be hard. It's got 3 variables. Wait a minute. Next one only has 2 variables. that triangle right there. Z equals 3. Cool. They gave me one of the answers already. All right, so I know Z equals 3, and I also know that three-dimensional systems are written as what's called an ordered triple. So far, we know this last number is a 3. Then I realized, well, there's only 2 variables in the middle one, and one of them is Z. So if I put what I know about Z in here, I can get Y. So Y minus 2 times 3 equals negative 7. Y minus 6 equals negative 7. We add 6 to both sides. Y is negative 1. Cool. Right there in the middle. Now, one more equation to go, and I don't have X. But the good news is I have Y and Z. So that's why this is called back substitution. It's just like we go one step back, and we're substituting in. So X minus 2 times negative 1 plus 3 equals 7. X plus 2 plus 3 equals positive 7. Not negative 7, that was the first equation. So X plus 5 equals 7. Subtract the 5. Then X is 2. A little too easy? That was like, here's a perfect example of back substitution, and using that triangular form to get it back up there. But sometimes we can do a little math and make it look like this, which then is really easy to just back substitute and go through. So that's what we're hoping to do. Now, this doesn't have all the little notes on there. Did you guys get the little notes where it says, notice the solution is in triangular form?
It's on the next page.
On the next page, okay. Well, no, wait for that. All right. So what happens? Oh, that's very through this back substitution is we get the answers. And sometimes, like I said, sometimes we have to do some math first to get it to look that way so it'll go faster. So with Gaussian elimination, we're going to transform a system to triangular form in Gaussian elimination. It's named after, of course, the guy that developed algebra by saying if it has an exit, it has an answer. The fundamental theorem of algebra was written by Carl Friedrich Gauss, and this was one of his methods. Equivalent system of linear equations. The following operations produce an equivalent system of linear equations. You can interchange any 2 equations in the system. So just move them. With one before the other two, and you can move them around. You can multiply or divide one of the equations by a non-zero real number. That's a scalar. So if we need to, we can multiply it by a scalar and get things to happen. And then add a multiple of one equation to any other equation in the system. We already know we could do that because we had things like this. We said, okay, yes, we'd like to use substitution, but if they forced us to use the elimination method, what we would do is say, well, I'm going to multiply this whole thing by 3 and add it to get those x's to drop out. So we've actually done that before. None of these operations are new to us. It's just that now we're going to have a little more to keep track of. So it just says solve the system. So here's what we're going to do first. We're going to pick one of these equations to be what I call the Terminator. Ever seen that movie? You know, the Terminator destroys everything else. Arnold Schwarzenegger and very bad pronunciation all the way through the movie. But we want the Terminator. So the Terminator is an equation that you could easily multiply by something and get rid of the other variables from the other equations. So I look at this one and I'm thinking, I want something that's really easy to multiply by, either to get rid of the x's, the y's, or the z's here. And there's a couple of choices with this one. Well, this x sure would be nice, because if I multiply this by a negative 3, I can make that one drop out. If I multiply this by a negative 2, I can make that one drop out. Some of you might look at the z's and say, well, I can multiply it by a negative 1 and it'll drop out right here. This one is perfect for just adding right away and getting the z's to drop out of that one. And it really is a matter of which one you see first. That's the one you want to use. So when you saw this, would you be thinking x's or would you be thinking z's? Z's? All right. Then let's use that top equation to eliminate z. And see what happens. So here's what we said we wanted to do. For 3x minus 5y plus z, the second equation, we need this to be a negative z. So I'm going to take my terminator times negative 1. And see what I get. There it is. Just changed all the signs. That's all it did. Now I'm going to color coordinate this, and you can certainly do that too. There's stuff in the bag there if you want. So my terminator is going to be in red. Whenever I work with this second equation, so that one I'm just going to go ahead and write down. And I want to add those together so that the z's drop out, which is perfect because they're gonna. We've got a negative z and a positive z. So negative x plus 3x is 2x. 2y minus 5y is negative 3y. Z's are gone, which is exactly what we wanted. Negative 7 plus 14 is 7. Okay. Well, that was the second equation. We also wanted to get rid of the z's in the third equation because we want to get one variable out of the entire problem first. I'm going to switch to blue here. But my terminator didn't need to be multiplied by anything to add to get rid of the z's, so I'm just going to write my terminator back up here. And then I'm just going to write down my blue equation, the third equation. And add those two together again so that I'm eliminating that z. Now I take a look and I realize this is stuff we've done before. I mean, now we're down to 2x minus 3y equals 7 and 3x minus 4y equals 7. We've done that before. So now I have to figure out, all right, what would be the easiest way to get stuff to drop out with these two equations? Bless you. So I'm going to move this over here and ask you. What do you think? Would you go after the x's or would you go after the y's? Because it's a 6, right? Yeah, 6 and a negative 6. So I would probably multiply the top one by a negative 3. And the bottom one by a 2. And that would give me negative 6x plus 9y equals negative 21. And 6x minus 8y equals 20. Which does exactly what we wanted to do. The x's are now going to drop out. And even better news, 1y equals what? Negative 1. Now we can back substitute. If we know y is negative 1 and we want to use this triangular form, the next place to go would be the next biggest equation, which are these two right here. And you can use either one of those to figure out, hey, what's x going to be if y is negative 1? We'll just use the top one here. So 2x plus 3 equals 7. We'd subtract the 3 and divide. And x is 2. Now, which of the original 3 equations did we say was probably the easiest to work with as our terminator? Because that's usually the one we want to go back to get the very last variable. So now we take our x equals 2 and our y equals -1. And go all the way back up to that terminator to see what we get. Find some room here to write down my math. So we have 2 plus 2 is 4. 4 plus z equals 7. Subtract 4, we get z equals 3. Question. You learn that method in Algebra 2. You might have had to cut that off. You guys remember solving 3 by 3s last year all? Yeah, I think we had to cut that off last year. So we used to, before all the standard stuff, be able to teach the 3 by 3s in Algebra 2. And it's not a tough process, but again, there's a lot to keep track of. There's so many numbers all over the place. And it is called Gaussian elimination. So we find one of those solutions and then we just back substitute twice to get all the way to that ordered triple that we need. Well, look at all that. I mean, not that that's not great math, because it is. It's beautiful. So, like it says, notice the solution is in triangular form and has exactly one solution. The leading term of each equation has a coefficient of 1. The third equation has one variable z. The second equation has two variables y and z. And then the first equation has three variables x, y, and z. So, in their weird way, what they're pointing us to is this. We start with this. We work our way down to two sets of two equations. And then further down to just, here's one variable. And then we back substitute into the two equations and all the way back up to the three variables that we have up here. So, Gaussian elimination. If there were a faster and easier way, would we want it? Of course there is one, and it's matrices. If we use matrices, it simplifies it a little bit, but again, it's going to be all about order. So what we're going to do with this one is it says every once in a while you go through all this math and you find there's no solution. Ouch. So let's see what happens with this one. I want you to take a look at it, and I want you to think about picking a terminator. First, second, or third equation. First one, okay, you thinking X's or Z's? Me too. I don't know why. You know, the Z's might, well, we got a 13 here. Probably wouldn't want to multiply by 3. So, my terminator. All right. So, here's my second equation here. What are you thinking we should do to the terminator to work with that second equation? Nothing. Not a doggone thing. So we have an x and we have a negative x. We're going to drop off very nicely. Negative y minus 4z. All right, I'm going to switch colors here. You have to switch with that, or you have to stick with the same variable. You can't suddenly decide, hey, I want to go another way halfway through the problem. So what are you going to do to your terminator for this one? Negative 5. Oh, let me see if I've got way to write this so that the notes will be followable. Okay, we'll do that. X's are going to drop out like we wanted them to. So far, so good. Y's, Z's. What are your thoughts?
Divide the second one by -2 to get the same answer, except it's not 7.
Ah, good idea. Do that. What else do you see? green and the black here. Multiply by 2. That's what most people will see. So let's go with that. Yes, I'm totally with you, Art. If you see that those are all divisible by 2 or even negative 2, go for it. But most people are going to say, hey, I'm going to multiply this by 2. Bring it over here and see what happens. And oops, what does happen? Is that possible? 0. So that's how we're going to know we have no solution. Not going to happen. 0 is not going to happen. So it was a lot of work to get, but we couldn't get a solution out of this one. So we can't do our back substitution. It happens, you know. So does infinitely many solutions sometimes. So we have to be prepared for it. So now, how could we make this a little more condensed and not have so much going on and still be able to find the answer? And that's going to be matrices. That absolutely will be matrices. So elementary row operations and what's called row echelon form. So row echelon form has this. 1s across the main diagonal and 0s everywhere to the left and below. That's row echelon form. Now, here's why that's something we want. It's because these columns are going to stand for X, Y, and Z. And what this one says right here is 1Z equals something when we get done. We're going to be able to use that to then back substitute or use what's called reduced row echelon form. So when solving a system of equations using Gaussian elimination, all the action is really on the numbers. The X, it just means the X's and the Y's and the Z's, they don't really matter to our solution. We could take them out of play, do all the math, and then put them back in. And that's the easiest way to do it, to keep track of everything. So if we have X minus 2Y plus Z equals 7, instead, just use the coefficients 1, negative 2, and 1, making your matrix. 3, negative 5, and 1. 2, negative 2, and negative 1, and putting those in there. But obviously, we want to find the answers. And that means the 7 and the 14 and the 3, they matter. So instead of just making a coefficient matrix, we make what's called an augmented matrix. And one of the things we want you to do is something that every other book I've ever studied on matrices does, and that is you kind of separate your coefficient and your augmented matrix by just a dashed line to let you know, hey, all of this stuff to the left here, that was my coefficients. So this was my X, my Y, and my Z. These were what they're supposed to be. Those were the answers on the other side. So here's what we're going to do. We are going to try and take this matrix, our augmented matrix, and make it have 1, 1, 1, 0, 0, 0, so that then we can take our Z answer and back substitute into the other two. But we're going to do it with the exact same math that we just got done using for Gaussian elimination. So, first thing we'll do, write down our augmented matrix here. Yeah, I don't want to skip a step. They've got us doing some stuff. I think we just keep going through. So 1, negative 2, 1, and there's 7, 3, negative 5, 1, 14, 2, negative 2, negative 1, and 3. Now they're going to guide us through this. It says multiply the first equation, which was everything on the top here, by negative 3. And then add that to equation 2. This one, instead of this one, why are we choosing this one? Oh, look at that. We were going to keep it the same. Mrs. Peters made another change. All right, so yes, you're right, Holly. Let's start with the new stuff here. We were going to do the exact same problem again. She must have decided she didn't want that repetition. All right, so 1x, negative 2y, 1z, 7, 0, 1, negative 2, negative 7. That's what happens when you're absolute. 2, negative 2, negative 1. All right, we're going to multiply equation 1, row 1, by negative 3. And then we're going to add that to row 2. Now, you might want to, just so you don't miss things, kind of do this in steps. So multiply equation 1 by negative 3, but don't write anything down yet. Just like put it up here. 1 times negative 3 will be negative 3. Negative 2 times negative 3 is 6. 1 times negative 3 is negative 3. And negative 3 times 7 is negative 21. So what we're going to do with those numbers, because we just multiplied that entire equation by negative 3, it says add that to equation 2. So you have all of those, add that to equation 2, which is row 2. So negative 3 plus 0 is negative 3. 6 plus 1 is 7. Negative 3 and negative 2 is negative 5. And negative 21 and negative 7 is negative 2. Now all that replaces is row 2. So my first row is the same.
System of equations to the left of that box.
Nothing right now. It's not following these directions that she has here. Equation 1 by negative 3. 3, 6, negative 3, 7. What did she do? Yeah, I think her directions are, her directions are wrong. Her directions are wrong. So let's do the steps together and correct. Did they have these on you guys' paper?
Yeah.
Let's just do this. Do that. Because it is definitely the hard way, the way that they had.
So, just the second row and the second page. Well, what I did, I just looked at this, put it in here, the coefficient. First, I was like, where are we coming from?
All right, so let's go back. Let's go back. The 0 is because there's no x here. That's where that came from. All right. So here's the easiest way to do this problem. We have a 1 up here, and this is a 2. What do we need this to be to add it to 2 to get 0? So let's multiply by negative 2. She must have just forgotten to change this. And add that to row 3 to eliminate this. We want this first number gone. Remember, what we really want is this. We want 1s and 0s in these positions. That's what we're working towards. The rest of it can be whatever numbers it needs to be. But we want it looking like that. That's called row echelon form. Once I get there, I'll talk you through the rest of it. Alrighty, so let's add this to the third row. We multiplied row 1 by negative 2, and we're adding it to row 3.
It's really easy.
It is, and I wish I had taught that before. See, mine are the old notes. I don't know why she made changes and didn't switch anything. All right, so now take a look. Aren't we super close to having 1s here? Super close, right? So we need to get this out of here. Now we obviously can't use this row because if we multiply this by something and add it to this row, now we put a number here instead of putting a 0 with it. So we're going to use row 2 to try to eliminate this 2. So what should we do to row 2 times negative 2. So this time we're going to do negative 2, row 2. And that would give us negative 2, 4, and 14. But we're only going to add that to row 3. So we'll have 0 plus nothing, 0. 2 plus negative 2 is 0. Negative 3 plus 4 is 1, which is perfect, by the way. And 14 and negative 11 gives 3. Other rows will stay the same. Now here's why we do this. This just gave us one of the variables. Look at the triangular form. This is x, this is y, and this is z. No x's, no y's, but one z equals 3. And now we can back substitute. So if we can get it into that row echelon form, we back substitute. And the obvious place to go would be the next one up. We've got 0 x's, 1 y, minus 2z equals negative 7. Let's take our 3. Let's put it right here. And then we just add 6 to both sides. Now we have y and z. And let's go back to our top equation in row echelon form. Again, it's always x, y, z. Occasionally you get a double where you have 4 variables. Plug in what we already know. And find x. And then we can write our ordered triple. So there it is, 2, negative 1, and 3. So yeah, that's really weird. Usually she changes the directions on there. Questions? Oh, sure. So our goal, getting 1s on the diagonal, 0s in these other positions, because then this says z equals something, and we can back substitute and go as far back as we need to get our x's, y's, and z's. So the augmented matrix, corresponding to the triangular form of the original system of equations, is in what's called row echelon form. Row echelon form. So that's what we were doing. 1s on the diagonals, 0s, everything to the left and below. Then back substitute to get your solutions. All right. So white out for next year's packet, I guess. Our goal is to take a system of equations, writing the corresponding augmented matrix, and transform it to row echelon form. Get it that way. And if they're huge matrices, we're not going to do them by hand. You know, if they're 4 by 5, 4 by 6, anything that's just a little bit too much, we're going to do a calculator. So from there, we can use back substitution to get the solutions to the system. So we could always go back, put that matrix into our calculator, and under matrix math, row echelon form is under there. So definition, row echelon form of a matrix. A matrix is in row echelon form if the following conditions are satisfied. Rows consisting entirely of 0s, if there are any, occur just at the bottom of the matrix. The first entry in any row with non-zero entries is 1. So 0s before the 1s. And then the column subscript of the leading 1 entries increases as the row subscript increases. Oh my gosh, they make that sound so hard. All we want to do is make sure we have 1s on that diagonal and 0s for anything to the left and below. And that will allow us to have things in row echelon form. So like it says, the leading 1s move to the right as we move down the rows. First it was in the first column, now it's in the second column, now it's in the third column. That's what we really want for this to be in row echelon form. And those row operations that we just did were elementary row operations on a matrix. They're the same thing we would do if we left all the x, y's, and z's in there. We just took them out combination of the following operations will transform a matrix to row echelon form. You can't just move two rows. You know, if you say, hey, this one already has a 0 in front, I'm going to put that down on the bottom. You can do that. You know, you're just switching the order. Multiply all elements of a row by a non-zero real number. That's a scalar. We've been doing that all the way through. Add a multiple of one row to any other row. Absolutely. That's what we were doing when we were just doing Gaussian elimination. So notation, it says we have an R, and that's some matrix that we have of I and J, and that indicates interchanging the ith and jth row of a matrix. So if you want to switch them, we do have some notation for that. K times R sub I indicates multiplying the ith row by a non-zero real number K. So this is if you want somebody to be able to follow your steps and you write down what you're doing. And then this one says, all right, if you're going to take a scalar times that row and then add it to another row, make it so somebody could follow. You know, as you go through there. And I can give you that notation as we go through this stuff too. But I better check this. All right. So we're going to take a peek at how far we'll be able to go. Oh, and I should let you know, some of them come up with fraction answers. There's only so many beautiful answers that we can get from all of these. Actually, these are really basic ones in the homework. We did not use the calculator yet, so you wouldn't be able to do the with calculator part. So write it down. It'll be something we'll be able to do tomorrow. So you can do the stuff by hand. What we have today. And before I leave, I will grab one of your packets and see if she reorganized anything else that can get printed. But everybody got those instructions that were in the blue off to the side scratched out, right? Okay, that way at least you can follow what you have.